My name is Ryan Brush, and today I want to talk about how we can make our code simpler by using some ideas that we see in expert systems. And then we're going to take a look at an open source implementation of these patterns in Clojure. But I think a lot of this, about what we're going to talk today, really applies to a lot of different programming problems in a lot of different languages. So we're going to start with a story, and the story starts in an era in which real computers were still moved around with forklifts. And it was in 1977, and we start in 1977 because that was the year that this man, Edward Feigenbaum, quipped that intelligent systems derive their power from the knowledge they possess rather than the formalisms used. And this, maybe it seems obvious at the surface, maybe it seems obvious today. But I think this opens up a number of deeper questions about how we should build our systems. And these are questions that I feel like we don't have a great answer to yet. So for instance, if the knowledge is the most important piece, how do we manage that knowledge so we can all make sure that we're all thinking about the same thing, that we have a shared understanding of this knowledge so that we can build upon and maintain it? Also, how do we manage the semantic gap, the distance between what the domain knowledge is and what our code looks like? And if that gap grows, if our code stops looking like what that expertise is, how do we keep that in sync? How do we enhance the code in order to stay close to what this expertise is? And really, if experts in a domain, if they think in these kind of composable units of knowledge, if they think in terms of information that we can build on top of each other, can we model how experts think about problems in our systems itself, thereby making it a lot easier to manage what the system does and how domain experts think about it? And this started to take off. This was a big problem in the late 70s. We'll skip to 1979, and that was an important year because this was the year that Charles Forgy published his PhD thesis. It's on the efficient implementation of production systems. And the key to that thesis is that Charles Forgy had an insight in that if we take rules that look like this, and then if you have many thousands of them working with many thousands or tens of thousands or more data elements, it simply isn't practical to run all of your data against all of your rules. So even if we wanted to codify knowledge in terms of rules, in terms of how an expert might think about the problem, we didn't have an efficient way to do it. So Forgy's insight was, well, in most domains there's commonality between these rules. Even if it's single expressions, there's things that we're evaluating over and over again. So rather than trying to run all the rules against all the data, let's take this, let's slice them up, and then build a network of commonality between these rules. So rather than dumping everything against every rule, only things that can match and data just flows through this network. And suddenly we could take very complex knowledge bases, we could codify that domain expertise, and we could run it really reasonably efficiently against these rule sets. And this is a big deal. I mean, this kind of launched an industry, and this industry really took off. It gained a lot of momentum, and perhaps rising to its peak in the mid-1980s in contexts that look like this. This is NASA's mission control. And in 1985, starting in 1985, NASA was running the mission control for multiple spacecraft, including the space shuttle, using these expert systems, using all this codified knowledge of all the inputs that we need to look at. How do we handle all these pieces of information in order to operate these incredibly complex pieces of machinery? So there was success on these rules engines caught momentum. They solved some really hard real-world problems. And of course, that success started to grow and led to some more excitement. Getting into the 1980s, rule engines, new businesses, new companies started to build them. The problem is that these expert systems, they usually didn't run on computers that look like this. They usually ran on computers that look like this. And this is a symbolic Lisp machine. The idea being that, hey, if we build hardware that we can run Lisp directly on, we can beat the performance of a more general computing. Turns out that wasn't really true. This was being undercut by much simpler computers, by much simpler instruction sets. And so this investment in these expert systems was being undercut. But that really wasn't enough to deal a really hard blow to these companies. What really is that they were overhyped. We can find material from the era. Here's 1990 from InfoWorld that, frankly, a lot of intellectually dishonest promises were made. We saw expert systems. We solved some problems with them. And then, as so often has happened time and time again in AI systems, that there's so much excitement builds up, and then we can't scale them. That led to the second AI winter in the 1980s. The first one was something similar that in the early 1970s. So our story continues. We'll pick up in the 1990s, and this kind of arc may look familiar, and it may look like the hype wave, where we have a new technology, excitement exceeds all reasonable expectations, and then we crash down realizing, hey, it's not going to do all that stuff. And then we'd expect, if it does follow, if rule engines did follow this sort of hype wave, we'd expect to be climbing back up it. We'd expect it to be regaining that momentum to make a practical use. And this happened. It happened sort of. And this is where I think our story took a wrong turn during that recovery from the hype cycle of expert systems. And I think part of the reason it took a wrong turn is that we have to look at what else was going on in that time period. What was going on in the 1990s? And here we have a graph of the employment level for people that call themselves information technology workers. I mean, it's kind of a broad group, but it's a proxy for what's going on in the trend. There was a huge demand for developers. There wasn't a supply to meet them. And this huge demand, well, it ended up creating essentially a secondary demand, in that if we could find ways to solve problems that may have required code, then yeah, let's do that. So we'll ignore the logical contradiction in this because, well, a lot of people did in that era as well. But it's really easy to look at, if I see this, if I see rule, when this, then that. I mean, it's like, do I need a programmer to write this? No. I mean, yeah, somebody can write this. And as an engineer, this even sounds a little bit appealing to me. I mean, as a developer, because trust me, I have no shortage of things to go do. If the business folks want to handle this piece of it, let them. I'm happy to do that. And Martin Fowler observed this trend several years later, in that the central pitch of rules engines has become allow business people to specify independently without involving programmers. He went on to say that this usually doesn't end well for reasons that we're going to jump into. And because this demand, our rule engines, our expert systems, their tools started targeting business users. It started rather than engineers. So we started seeing these very limited mini languages emerge in order to express our logic, or even decision tables in spreadsheets. And sure, if you have a simple problem, if you have an example problem, and even some constrained use cases, it can work great. And if we're living in that world in which a decision table and a spreadsheet or a really simple language meets your needs, then great, we're set. The thing is that those problems usually don't stay simple. And so we end up with things like this, where we have a tool that targets a business user, and we end up with a pile of Java, if a pile of Java code, then another pile of Java code. I mean, what did we really buy ourselves here? We said we're writing Java with a .drl file now. It doesn't really buy us much. And then similarly with this, putting in decision tables. I mean, it looks clean. I know you can't read the specific text in there, but I mean, if you could, you would see that. Yeah, that's Java code in an Excel spreadsheet. There's a couple other examples of it. So I don't think that anyone woke up one morning and came in and a green password problem says, everyone, I figured it out. We can solve this problem by writing Java code in Excel. I don't think anyone actually ever did that. But I think that what this does is, this is a workaround. This is a workaround that tells us that the approach that was taken to solve this class of problems isn't optimal. It says that there should be a better way. If you end up, find yourself in a position where you're writing Java code in an Excel spreadsheet, you're probably going down the wrong path. And the fact is that rule authoring, well, you know what? It's development. It is, what's the difference between a rule and a function? I mean, even if it's in a trivial sense, even if it's a simple rule, it's development whether we call it that or not. So what if we turn this on its head? What if we take this approach, take this industry, demand arose to write code without developers, and we kind of lost our grasp on these expert systems as programmers. So let's turn it on its head. What if we approach expert systems as code? So a lot of times when we write code, we can think of, we have some data. Let's here we have A and B. And then we'll do some sort of transformation on this. Now, in some languages, these transformations may be update something in place and put in a new value. In a functional language, it'll take these inputs and produce a new outputs. It doesn't really matter that much in this context. So much of what we do is we take inputs and then we build on them and we emit something else. And this applies to a lot of domains, whether it's we're doing expense reports for traveling, might have to account for a contract budget and justifications, or if we're putting together a sales package, we might look at their history. Or in the domain that I work in healthcare, we have a whole bunch of inputs to determine, hey, what sort of plan of care that do we need to live in, do we need to deliver? So this is applicable in a lot of places. But our challenge is we have to wire these things together. And this gets a little more involved. I mean, right here, this looks pretty simple. But when we start wiring everything together, taking all the inputs from one function, wiring them into the inputs of the next, and composing it. And then once we even have all those wired, it gets even more complicated, because suppose we introduce some new input. Suddenly I'm rewiring a whole bunch of my functions. And if you're in a domain in which your nested functions only go a couple deep, you can go through this. You can refactor your code. You can pass the data that you need to the function that needs it. But then we get into these worlds in really complex domains in which our functions are many layers deep, and suddenly I want to pass something into something that's deep down in there. And then, so you're suddenly refactoring your code and making sure everything's there, or doing something truly hideous and you're creating like a global variable or something like that just because you can't touch all the code. Or we don't have a great solution. I'm a big proponent of a functional approach to programming, but I feel like we still can our code can still get tangled even with this functional approach. And if we try and do this with thousands of requirements for different sources, it gets really complicated. And it just comes down to the fact that this explicit wiring, this way of tying everything together that we have to do by hand, is error-prone. And so let's ask ourselves, can we do this automatically? Can we wire these things up automatically? So let's look at this and ask how we could do it. The first thing that we notice when we look at this on the left side of the screen is that how these functions should be wired is actually unambiguous. We can see that when we emit something new, we can see where it gets wired into the other one. And since it's unambiguous, it should be able to automate it, right? And so what if we described this set of functions as these units of logic, where every input that we take specifies a type, and that type could be whatever type system exists in the host language that you're working with, and a set of constraints to say what subset of the data that you're interested in that function. And we're going to dive into how that's possible. But really, and this is essentially looks like a rule like you might see in an expert system, but applied in a context of in line with the rest of our code base. And this is so really we're viewing rules as a type of control structure, something that we can integrate it in with the rest of our code in order to simplify all this nasty explicit wiring that we have to do otherwise. And now I want to look at how we could actually apply this, how we could implement it. And so I'm going to take a look at what I'm calling a principal design for rules as a control structure. And by this, I think that if we can take a few premises, a couple basic assertions, we can come up with a design for how we could implement rules and make it a first-class participant in our development process. So we'll start with really the proven model. This is how expert systems generally work. We'll have a working memory which contains all the knowledge that our system has. And each unit of knowledge is typically referred to as a fact. So the fact that Alice has hypertension in the healthcare domain, that would be a fact, a unit of knowledge. Then we match those facts against a knowledge base. So if Alice has hypertension, then we might prescribe some medication. And then we can infer new information, say the medication that we should prescribe. And then this goes in a cycle until the system normalizes and we have all the derived information in our working memory. So in code, we can map this to code. We have a simple unit of logic. In this case, it would basically be a rule. Every input has a type, and we can apply this to whatever type system the language exists that we're implementing this in. So even dynamic languages, even if it's a dynamic type system, we can match, hey, how should we wire up our inputs? And we'll go into examples of how we can do this. We want to specify the constraints for what subset of input. Maybe I'm not interested in everything that matches a certain type, but only things that match certain criteria. I'll show examples of that as well. When our function fires, we want to unify the perspective, unify the input of it. So, for instance, if we're looking at lab results and say some sort of medical history of a person, if we have multiple people in our memory data, we want to unify it. We want to make sure that both the lab results and the medical history are looking at the same person. And you can apply this to any domain, whether, we're talking about healthcare, but things like if it's a customer and an order history, just almost anything we can apply this pattern to. But this gives us a consistent view of the data that's passed into our function. And then finally, we can have arbitrary actions that fire on the right-hand side. And then the last piece that we see in these expert systems is truth maintenance, where if it's true that if we have some data element that A asserts that B is true, if A becomes false, if they no longer qualify for some reason, we want to retract that particular piece of information from the system, so to keep everything in a consistent state. And so this really brings rules as a first-class participant into our development process. And there's actually a few systems out there that follow a pattern that's similar to this to varying degrees. So Nulls is a nice JavaScript version. It uses some pre-processing logic. There's Wongy and Ruby. The one we're going to focus on is Clara, a Clojure implementation of this pattern. It's open source. It's out on GitHub. And I'll have a link at the end of this talk. And I think that Clojure is actually perhaps uniquely best positioned to tackle this sort of problem. Part of it is that it emphasizes data over objects. So if we have, as we write rules and expressions, we want to easily access our data versus having to dig through some object model. Equality means something, and I'll show an example of why this is important when we jump into the code a little bit. In that Clojure has well-defined equality semantics for all types, and really, if you're working with any form of logic programming, and just something as basic as saying whether two things are equal and knowing that they will always be equal and not being able to mutate them underneath us, really simplifies how we can reason about our systems a lot, and we can leverage that extensively by doing this in Clojure. Clojure has great reach in terms of the JVM, and the system that I'll show here also compiles to JavaScript, and we can use, via ClojureScript, it compiles to JavaScript. And then we can also plug into Java beans in this system, assuming they behave well, and that you don't mutate them underneath the rule engine. And really, and the biggest thing is the ability to grow the language of Clojure. And this is in the sense of Guy Steele's famous growing a language talk, in this case, using macros. So if we look back, we can look back at those rules we have. And this is actually valid syntax in Clojure, so modeling those very simple hypertension rules. And the way that this system works, the way Clara works, is it essentially, by using macros, that we can take these declarative structures and transform them at compile time or just before runtime into this same Reedy network that Charles Forgy posted. Now, Reedy has evolved quite a bit over the years. It's not exactly an implementation of his paper. It works in collections of data elements rather than individuals. It'll build indexes in the nodes, but it's still that same basis of building a rules engine on top of these simple infrastructures. So with that, we're going to take a quick look at some of the code here for what Clara does. So skip out of that. All right. So this is just a valid Clojure file. There's nothing unique about this at all. Nothing special about this. Requiring just some things that we'll use in the demo. Early on, these are just some records and some functions that I'll use below. These are all defined using the prismatic schema library, just because it's nice to have clear what clear definition of what your structure looks like, but we don't need them to be prismatic schema records. They can be an arbitrary Clojure data structure that we can destructure in arbitrary ways. And as I mentioned a little bit ago, they can also be Java beans. So let's take a look at the first rule. And in this case, we're simply saying, hey, if a blood pressure between these ranges, then we infer that this person is hypertensive. And what we see here, this is actually is an indication that it binds the person ID to this variable, and so thereby making it visible on the right-hand side of our rule. And it's also used for unification, as we'll show below. So this another rule basically does something pretty similar, looks at a different range. Now, this is where we start getting a little more interesting. One of our big challenges, like in code in general, is how do we make things composable? We're good at thinking about things in individual pieces. If I don't have to juggle so many balls, I can only juggle so many balls at a time. But in this case, what we can do is we can compose rules on top of other ones. So if I assert that somebody is hypertensive, in this case I can catch, hey, this person is hypertensive under certain criteria, and use that in some rule that builds on top of it. And this assertion for I'm recommending some medications, this may be picked up by some other rule. The other interesting thing about this one is we see an instance of a very simple instance of unification, in that here we have a variable. By convention, we use a prefixed question mark on the symbol name to indicate it. But here we bind person ID to this, and here we bind it to the same thing. The rule engine will ensure that these are unified, and so if I have rules from multiple people inside the system, we'll be ensure that each invocation only gets only gets that one person ID. And in this case, we unify on just an identifier, but we can really unify on any arbitrary structural type. And that's one of the advantages of the fact that equality means something. It's like you can unify two things because they are equal, and that has well-defined semantics in Clojure. And the other thing that's interesting to point out is that, these unifications are actually, these are done by parsing the code and detecting the need for unification, but everything in here is just a valid Clojure expression. So this is just a Clojure or expression. Here we're looking for people over 60. So this is a Clojure function that I defined up above. The particular data elements that are visible here. So by default, what we'll do is we'll look at the fields of the record and then make those visible to the context of your expressions. If you have a more specialized need, if I know your way around Clojure pretty well, we can do arbitrary destructuring of the facts and to make it visible to the functions as well. And then the right-hand side again is it's a Clojure expression. And in this case, it inserts some derived information, which is a pretty common pattern to just simply do an insertion of this new information. We can also do side effects as well in use cases where it makes sense. So maybe you might have a function here that says fire alarm or something like that, and then we can deactivate that alarm when useful. So I'll just browse through the next few rules, but you can kind of see that these are all composing on top of it. We take some of our previous information and we build on top of that, where we were determining whether if we can determine if this is a high-risk patient based on whether they have a referral and then chronic kidney disease. And by the way, this is completely fabricated rules. Do not take medical advice from this code. But it shows the examples. But so let's look at this in action. And so really what we can do is that for make session, it just creates a new rule session. If you're not familiar with Clojure, this is the threading macro. It'll just thread the output of one function into the next one. So we can make a session. By default, this is a macro. It'll actually load all the rules in the current namespace by default. You can pass in a sequence of namespaces as an optional argument to this if you want to load rules from a bunch of namespaces. So here we create a session, we insert some facts, we fire the rules, and then we run a query to, in this case, up above, we had a query that recommends medications, and then we spit that out. So we'll go ahead and, here, I'll make a little more room at the bottom here. So if we go ahead and run that, you can see that our query returned, for person ID 1, I just used 1 for all the person IDs here, and then it returns, hey, we infer this person needs a medication of lisinopril. So that's the simplest example. The other thing that we can do following this pattern, since we are basically making rules as a control structure in a host language, we really want to participate as a first-class entity in that. We want to follow the idioms, the best practices of that host language. And Clojure values immutability really strongly, which I think is important. I think that everything's trending towards immutability. And so we follow that here in that what I can do is I can define a session and insert just a little bit of data. Now if I run a query against that, it returns an empty sequence because there's nothing that matched. There's no recommended medications. But here's where it gets interesting. I can take my initial session, which I've just defined up above, insert some new information, then fire that. Now if I query the second session that we get, we have that recommendation, but the first one is unchanged. And so everything that we do, every modification, every assertion, everything we do to the working memory isn't really modifying that working memory. It's a pure function. It's producing a new working memory with that shared information. Now, it shares a huge amount of state internally, so this is actually efficient. Clojure has great structures, great persistent data structures in great ways in order to make transient changes to them as well. So it turns out that even though we're logically creating a new working memory, I've profiled this for a number of use cases. It's actually performance is pretty equivalent to Drools, even with the mutable working memory state. And so I think that's frankly as much a testament to the Clojure data structures that this is even possible. And then similarly, since equality means something, if I want to retract a fact, retract the unit of information, I can just create a new one and retract that. And since this blood pressure equals that previous one we had in the information in the working memory, it will just retract that based on equality. I don't have to deal with object handles or things like that, or external references to the units of information I have. If two records are equal, we view them as equals, and it just seems like a really simplified way to thinking about the problem. And then and since things are immutable, a common pattern is that we can actually just create a session with just our knowledge that's empty and then just reuse that. And we can reuse them as normal functions. So here's a normal Clojure function. It accepts a sequence of person data, which is can be their medical history, and it returns their recommended medications. So a consumer of this function doesn't even need to know that it's using a rule engine at all. And so this is how we can participate in a larger ecosystem. We can still build functions that use rule engines internally. It's all Clojure code underneath. There's no additional artifact to deploy or manage. But then we can take that advantage to simplify our code. So if we run this example function, we see that list, and we do a little manipulation in that function. And functions this one just does a pretty simple query and return some structure, but functions could do multiple queries, do additional processing. I mean, really whatever you need to meet the needs of your domain. And I'm going to touch on one more thing before we get back to the slides, and that the rule structures are actually also data, in that if I print out the context of a rule structure, this is just a Clojure structure as the documentation, the rule name, the left-hand side, everything in it. And so the implications of this is that one is that we can create tooling to explore our rules, but also if we have a complex, if I want to implement my logic using some higher level expression, we can actually generate these rules. And this is actually a pattern that I've seen a lot. I've seen a lot of people writing code that just generates rules versus some being produced from sort of higher level domain specific language. But we can do the same thing here, except instead of just kicking out strings, we're emitting a data structure that defines those rules, which then get picked up by our rule engine. And because it's a data structure, we can do some inspection of it. So I'll make this go away. So in this case, I created a session that inserted some information. But how often, when working with a really complex domain, do we have users asking, well, why did this input occur? Why did this happen? So what we have here is that since the rule engine maintains why every fact was asserted, why everything was inferred, it has to do that in order to maintain its consistency. We can actually print out explanations, and this is a little challenging in this. I'll make it a little bit smaller there, but you can see that here we have blood pressure with chronic kidney disease matched because this hypertension matched that type under this expression. And then if you wanted to track down, why, how we inferred this unit of information, we could go trace that back as well. So so I think this could be valuable in that one of our challenges is explainability. When working with really complex systems, how do we explain to the end user? And so I'm going to show this, which is a bit more experimental, so don't read too much into it. But this is really a web visualization of that explanation. So I click on the hypertensive fact. I can see that we inferred that because there was a blood pressure that matched this criteria that then inferred this piece of information. We can look at something a little more involved. So recommended medications. This can be hard to read, where we can see hypertensive inferred this, and we joined it with this demographic information and thereby asserted that. And yeah, these are all, this is more of an experiment at this point, and we're exposing the Clojure S expressions. But you can imagine tooling if your users don't like reading a prefix notation in Clojure, you could easily convert these to an infix notation. You could provide the user a visual explanation of why the system emitted the data that it did emit. And frankly, this is a lot better than having engineers logging in, choking around, trying to solve, trying to explain to the user. If we can provide a sort of self-service explanation by codifying the business needs in these rules engines, I think that there's some potential that we can explore there. So I'm going to go back to the slides a little bit. All right. And then a bunch of other things that I didn't show for the sake of time in terms of arbitrary expressions accumulators. I wanted to touch on one other thing as well, in that I said I'd circle back to Edward Feigenbaum's quote, in that they derive their power from the knowledge they possess. Now, a lot of times we might think of it, the knowledge they possess, we hope that we all have the same mental model in mind. We all see the system the same way. But in practice, language is ambiguous, right? Everyone has a different thought of the system, a different view of it. And I think this is really one of the great advantages of an agile development methodology. I think this is why these things one of the things this approach has gained attraction, in that if people have different perspectives of the system, by iterating on it, we can slowly converge these perspectives. We take some sort of minimal product, we build that, they say, yeah, that looks good, this doesn't look good, and we build towards that shared understanding. And that's a good thing for Agile, but sometimes you have to step back and think, imagine if other industries use this same approach. I might get an ambiguous description of a building. It's like, oh, no, that's not right. We really want it to be shorter, or like that. And then they put this, and it's like, no, we really wanted it to be green. So we'll just go and drop that. This is actually how we build software, right? And it works. It's actually a good way to build software in a lot of cases. It's a good way to build software when agile development is cheap, when iteration is cheap, and that I can quickly iterate and improve these systems. But our challenge is that iteration isn't always cheap. And I'll take a look at this. So this is an actual, I didn't make this up, and there's no way you can read it, but it's actually I have to read it myself, the Integrated Defense Acquisition Technology and Logistics Lifecycle Management Framework. Yeah, this is real. Can you imagine being given this and asked to implement it? And we could take an agile approach. We could carve off some minimal viable system. We could do that. We could write unit tests for that system. But does that really help us? Because we're writing unit tests for the developer's understanding of the system. We're not writing tests for the end users, what they desire. And yeah, we could take the minimal system and give it to the end users and have them click through it. But are they going to go through every permutation of logic flow in this system every time we iterate? I think this is a challenge. And Agile is a challenge when we have this really deep complexity that's not on the surface, that's not easily visible to the users, where the unit test we don't really know, it only validates the developer's understanding. So we have to ask ourselves a question in that, what can we learn from industries where Agile doesn't work? And there's a metaphor there. There's a metaphor where we have blueprints in these other industries, where and this maps to our code, that maps to it's an unambiguous specification that describes our system. But as a layperson, I can't really look at a blueprint and make sense of it. It doesn't help me understand whether the building is or isn't what it does, what I want. But the construction industry does have a model that helps me understand, and it's a floor plan. And a floor plan, what is it? It's really just a simplified projection of a blueprint. It's something that I can look at and say, hey, I like that room. We need to make this one bigger. It's something that we can use to build that shared understanding, to make sure that the building blueprints, the building design looks like what I want it to look like before we begin the construction. And that asks ourselves the question, can we learn from this? In instances in which agile development may struggle, can we create some sort of floor plan metaphor in software? And so this is where we're going to take a look at something that along these lines. So let's go back to our rules. And so taking all the logic above, what if we created a visualization of our logic that users could interact with? So actually this is by itself. I'll zoom out to show the kind of complexity. So this is the complexity of the rules and their relationships. I mean, so this alone, we're not going to make much sense of this. But the nice thing is that since all of our logic, since our rules are data, we can manipulate that. So let's say I wanted to zoom in on that, particularly how medication recommendation occurred. So suddenly I have something that's more manageable. I can see from blood pressure would infer how they're hypertensive. If all of the above criteria are met, I fire this rule, which recommends medications. And then we can, just for fun, I made some simple interaction with it so I could drill down and look at the source code if I really wanted to see what the relationships of these rules are. And I can zoom out and we'll look at another example here. If I want to look at something a little more involved, where I want to look at whether this person was a high-risk patient. Oops. And then we can see the relationships between those. So, and this is something that we can play with, but the nice thing is that by expressing our logic as rules in a language using a model that our users can understand, we can get a lot closer to creating these type of things, where it's a floor plan, it's a simplified description. Maybe it's a static document we generate. Maybe it's some sort of interactive exploration of data. But the nice thing is that by codifying them in a model, in the terminology and the rules that domain experts understand, we have the opportunity to start creating these artifacts. And this, I think, really what it boils down to is a sort of a new role for rules in our development process. In that rather than thinking of rules as something that's targeted business users exclusively, let's look at them as a tool for developers, a way that we can simplify our code. Let's look at them as a way to minimize that semantic gap. I mean, the closer our code looks to the actual desire of the business, I think that makes things a lot easier to work with, a lot easier to manage, a lot easier to reason about. And I think that they're also a leverage. They're leverage for shared understanding. They're a mechanism, a leverage, something that we can leverage to create these floor plans to share with our users so we can make sure that we have this common understanding of the system. And I think that probably most importantly, if you take away anything from this talk, I'd have to say just don't write Java code in Excel. And with that, almost out of time for questions. So I think that I'll just be up here if anyone wants to have a discussion. I would like to thank, this started as a side project. I would like to thank Cerner because we're starting to work on this and use this for the systems we build at Cerner too. It's great fun and we are hiring. So if you have any questions, I'll be up here. Otherwise, thank you.